So let me start my presentation. As Christian mentioned, looking at recycle or recover creosote from railroad ties and also producing biochar at the same time. So in the US, we have about 150 million railroad ties right now in use, of which 93% of these railroad ties are from wood. Most of the wood are hardwood. One example is quercus or oak. Out of total ties of wood, about 98% are treated with creosote. The reason that creosote is used is as a preservative for these ties. So when the ties are new, they have about 9 kilograms of creosote per tie. And with this treatment, as I mentioned, this creosote is used to treat wood. The life cycle of the railroad ties are between 20 to 30 years. Whereas if the ties are not treated, they last between 4 to 5 years. So the railroad industry needs to treat the ties in order to last long. So it's a necessity for them. Every year in the United States, about 15 million railroad ties are replaced. After the life cycle, there's ties or spent ties, when they are being replaced, they have left about 65% of the creosote, roughly speaking, about 5 kilograms left. Most of the spent ties are used as fuel and other commodities in the States. However, 5% of these ties may end up in landfills, which is not a good scenario for the industry nor the landfills, because to start with, the railroad industry pay about $8 to $10 of disposal fee per tie, and that was 3 years ago. And that doesn't include transportation. Maybe transportation might be cheaper or free, kind of free for the railroad. But still, there's kind of spending money on disposing of these ties. Also, it's a burden for the landfills because ties are relatively big, and they capacity of landfills is not, they're going to fill really soon. So again, we want to find ways to use these railroad ties and have a different use. So I talk about creosote-treated railroad ties. So what's creosote? Creosote is a distilled product of wood or coal. And as I mentioned, creosote is used to preserve wood. 95% of weight of the creosote is accounted for polycyclic aromatic hydrocarbons. And these polycyclic aromatic carbons, or pHs, are considered of environmental health concern. These pHs range from 2 to 10 fused rings, and the right we have few examples of them. We have naphthalene, phenanthrene, anthracene, fluoranthrene, pyrene, and benzoypyrene, which ranges from 2 to 5 rings. Also notice in these structures that solubility is very low. This solubility is in water. So as the number of rings increases, solubility decreases, which is expected. So one of the characteristics of these pHs is that they have very low water solubility. Also because the benzene rings and the fused rings altogether, they have a slow degradation. And as we increase the number of rings, the slower degradation of these compounds. The pHs in creosote are mostly 2 to 3 rings, and so they account up to 88% of weight in the creosote. And 52% of these pHs are the naphthalene, methylnaphthalene, phenanthrene, and anthracene. So there is different ways to recover creosote from spent ties, and the extent of recovery of creosote depends on the process used and the temperature that has been used during the process. So there are at least 2 of them that have been used. One is thermal desorption, in which 20 to 70% of the creosote is recovered. For the thermal desorption, between 15 to 30 minute resting times is used, and temperatures from 250 to 300 degrees Celsius. Pyrolysis process records from 60 to 70% of creosote using temperatures from 400 to 600 degrees Celsius. The above processes, thermal desorption and pyrolysis, recover or produce between 25 to 60% of biochar. However, whatever some of the residual pHs in biochar can range from 0.3 to 1.2% weight. So the objectives of this research working on this area is to use spent creosote-treated railroad ties to recover creosote to produce biochar material with a minimum creosote, and to investigate sorption capacities or capabilities of these biochars. Methods. So we use the pyrolysis process to recover biochar, creosote, from spent ties. And we use 3 different temperatures of pyrolysis, 500, 600, and 700 degrees Celsius. And for our pyrolysis, we use 0.5 grams of kilograms of 1 to 5 centimeter long shredded spent ties. And these 0.5 kilograms were placed in a split tube furnace with a coarse tube reactor. And we ramped the temperatures to 5 degrees Celsius per minute. So the first step was to ramp the temperature to 150 degrees Celsius and hold it for 30 minutes. The next step was to ramp the temperature to 300 degrees Celsius and hold it for 30 minutes. And last, we ramped the temperature to the final temperature, which was 500, 600, or 700 degrees, and to hold it for 1 hour. The pyrolysis process was performed under natural gas to minimize oxidation. And the fumes during pyrolysis were collected as condensates with a cold trap. So we performed some analysis on the products that we obtained from the pyrolysis. More specifically, I'm presenting here the 700 degrees Celsius pyrolysis processes. So we did extracted the creosote compounds using the pressurized solvent extraction technique from spent ties and biochar. Basically, we used 2 grams of the material, either spent ties or biochar, and 7 grams of sand. The sand was used as a filler. The solvents that we used in this pressurized solvent extraction was 1:1 volume to volume dichloromethane acetone, pressure 1 megapascal, and temperatures 100 degrees Celsius. The extracts from the above extractions and the condensates that we obtained, we analyzed it for 83 semi-volatiles using the GCMS. Also, we conducted toxicity and leachability tests using protocols from the United States EPA. And also we did some sorption isotopes with biochar phosphate and biochar nitrate. So I'm going to present some of the results. To the left, we have the prioritized raw material, showing just the 1 to 5 centimeter length. In the middle, we have the pyrolyzed railroad ties, so the biochar 700 degrees Celsius. And to the right, we have the condensates, the fumes that were condensed. And here we can see 2 layers. The lower layers darker and heavier, but also less amount than the upper layer. So doing a mass balance of our pyrolysis temperatures that we use, we notice that we have in this table the biochar, the upper and lower layers, and total recovery. The number in parentheses is the standard error, and the N is the number of runs with it for every temperature. So biochar produce ranges from 21 to 28%. The upper and lower layers combined range from 45.6 to 48%. So the total recovery of biochar plus the condensates range from 60 70.7 to 70.7%. As you notice, biochar production, condensate recovery, and total recovery decreases as we increase temperature. However, when we did some statistical analysis, we did not find any significant difference among the recoveries of the biochar or the condensates. So now let me talk about the spent ties and analysis that we performed. So out of the 83 semi-volatile compounds that we analyzed for, only 28 were detected. These 28 compounds vary from 1 to 6 rings. And total, we quantified 31 grams of semi-volatile compounds per kilogram of raw material. Out of these 28 semi-volatile compounds, 16 compounds are listed in the US EPA priority list pollutants. So these 16 compounds accounted for 93.8% of total weight of what we obtained on these spent ties. Most of it are 3 or 4 ring compounds, and these compounds were phenanthrene, pyrene, and fluorethene, and only 5% were accounted for the 5 and 6 ring compounds. Again, these are talking about the US EPA priority pollutant list. The heat of combustion of spent ties were 15 megajoules per kilogram. Let's compare that to propane, which is 50, and diesel, which is about 45 megajoules per kilogram. Condensates, as I mentioned in the beginning, we condensate the fumes during pyrolysis, and also we noticed 2 layers of the condensates, the lower layer and upper layer. So the condensates accounted for 46% of weight of the total spent tie. The lower layer, as I mentioned, is a darker, heavier than the upper layer. And the lower layer accounts for only 70% weight of the total condensates. The quantity of semi-volatiles in this lower layer was 367 grams per kilogram of the condensate. And like the spent ties, most of the compounds were 3 and 4 rings, which accounted for 88%. And as the spent ties, the prominent compounds were phenanthrene, pyrene, and fluorethene. The upper layer only had 0.6 grams of semi-volatile compounds per kilogram, and 79% were 1 ring compounds. I have to mention that no other analysis were performed to determine non-compounds in the condensates. And the heat of combustion was 32 and 4 megajoules per kilogram for the lower and upper layer, respectively. Biochar, for the 700 degrees pyrolysis processes, we produced 21% of weight of biochar and only 20 milligrams of semi-volatiles per kilogram of biochar, which is very low. Only 7 semi-volatile compounds were detected, and these compounds vary from 1 to 3 rings. However, which the good news is that out of those 7, only 5 compounds are listed in the EPA priority pollutant list. These 5 compounds account for 58% of the total EPA priority list in here and for this biochar. The surface area of this biochar was 152 square meters per gram. And we can compare that with other biochars in papers, and which is between 500 to 700 sometimes square meters per gram. The heat of combustion of biochar is 31 megajoules per kilogram. And then here we have an example of some chromatograms. And the lower left corner, we have the standard of 20 ppm for the 83 semi-volatile compounds. And also I have 5 internal standards. On the top of the standard 20 ppm, we had the rotatize, which is somehow a messy chromatograph chromatogram similar to the standard 20 ppm, and it's expected since we have 83 plus 5 internal standards, so we have 88 compounds in here in less than 20 minutes. To the top right, we have the 700 degrees Celsius biochar. And you notice we have 5 large peaks, and which those are the internal standards, and very small peaks, which are the semi-volatile compounds. The bottom right graph is a lower layer for the condensates, and this one has most of the semi-volatile compounds. And again, similar to the standards and the railroad is messy because of the compounds that we have. But again, using the GCMS, it's easy to determine and quantify the compounds. So let's think about mass balance of the 700 degrees Celsius pyrolysis processes. So in total, we recover 87.4% weight of the priority pollutants that the spentite has, of which 87.2% were accounted in the lower layer, 0.2% were accounted in the upper layer, and less than 0.01% was in the biochar. So what is that 2.6% weight unaccounted mass? That could be due to water losses and spentite, could be also to the condensation of the compounds in biochar during pyrolysis, or also could be other compounds that we did not analyze for. So I mentioned in the methods we did analysis, toxicity and leachability tests for biochar and the railroad spentite, or the spentite. So when we did this toxicity and leachability, these tests are meant to mimic acid rain and also landfill conditions. So we did not detect any semi-volatile compounds in biochar when we performed this test. However, we detected up to 0.34% of semi-volatiles in the spentite. No 5 or 6 ring compounds were detected, and we also detected copper in the leaching test from the spentite. Sorption capacity of the biochar 700 degrees. So currently we're working on these sorption isotherms, and the way we perform these sorption isotherms, we ground the biochar and use from 75 to 150 micrometer size char. And we use a 1:1,000 solid to solution ratio, shake it for 24 hours, and then we filter with 0.45 micrometer cellulose filter, and then analyze. So what I'm showing here is just prelim data. So after the sorption, the 24-hour sorption shaking, we analyzed, so we analyzed for pH. So pH was between 7 to 8. The electroconductivity between about 30 microsiemens per centimeter. So for the phosphate, we use from 0.5 to 20 ppm standard solutions. And we couldn't, after the sorption of 24 hours, we could not account for 7.9 plus minus 5.1%. For nitrate, we use from 0.5 to 20 ppm too, and we couldn't account for 4.8 plus minus 5.4% of the nitrate. So just looking at these numbers, I'm not surprised seeing the low sorption of these biochars for these compounds, because both of them are anions. Secondly, biochar 700 degrees, pretty much we remove all the reactive sites in the biochar, or the surface of the char. Also, we use a very dilute solid to solution ratio. We use 1 to 1,000. So again, I'm not surprised about this data. So what is the biochar issues and opportunities I see from our data? So I think our biochar have a low surface area. Could be because we use 700 degrees Celsius to recover the creosote and also to produce biochar. So we know that the higher the temperature, the lower surface area. From my perspective, biochar is not really available as a soil amendment at a large scale in the US. For example, typically when we do soil amendment biochar as a research, we found literature that rates of biochar applies for 0.5 to 2% weight basis. So we think about 1 hectare and 15 centimeters depth. We're talking about 2,000 tons of soil. So if we do the math using 0.5 to 2% weight of biochar, we're thinking about 10 to 40 tons of biochar per hectare, which at least in the Midwest in the United States is not feasible. I don't see it feasible. In addition, that farmers here in the Midwest, the United States have large farms. Could be from 200 hectares to up to 3,000 hectares. So again, looking how much biochar they need is almost impossible. Second, we tell farmers to implement minimum tillage or no-till at all, so to improve soil health. So doing that, then biochar has to be surface applied. As we know, biochar is light in weight. So when we have high winds, we don't want the biochar to drift, nor when we have heavy rain events, we don't want the biochar in the runoff and end up in lakes and rivers. So again, from my perspective, I don't think that using biochar as soil amendment in the United States Midwest is feasible. However, there's other possibilities using agricultural systems. Could be in different systems, for instance, in small gardens and greenhouses, things like that, where small amounts are needed. Also, we can use biochar as a carrier for fertilizer. And for water quality purposes, lower amounts of biochar could be needed only, and not great amounts like soil amendments. So there is several potential feedback sources that I see for biochar production. At least in the United States, as I mentioned in the beginning, 15 million railroad ties are replaced annually, of which 5% end up in landfills. So also in the United States, we have 180 million utility poles, which are being used for electricity. But out of these 180 million, about 30% are creosote-treated utility poles. So why not use this spent creosote-treated wood to produce biochar and recover creosote? By doing that, we have added value products. So that way we can recover creosote as a fuel and also production of biochar for different uses. Also, we have lessened the burden for landfills and industry. Something that I don't know anything about is economic feasibility for this type of work and make a large scale. So I think economic studies are needed. So future work, we are currently working with Sorption, as I mentioned, some capacity biochar. So we continue doing the nitrogen phosphate sorption. I want to use cadmium as a proxy for trace metals. I want to use atrazine as a proxy for organic pollutants, and also looking at PFAS sorption and biochars. We are going to continue the analysis of the 500, 600 products that we obtain from the pyrolysis. So basically, we want to see what the creosote recovery, what type of compounds we have, and also how much creosote is left in the biochar. Also looking at custom-made biochar to target specific compounds, because not one biochar will solve everything. And also use biochar as a carrier for slow-release fertilizers. So with that, I finished my presentation, but I want to thank my collaborators, Peter Ray from the Indiana Railroad Company, which provided the spent tide and gave us ideas. Also from my USDA collaborators in Peoria, Illinois, which they created and get the condensates for us and did some analysis. Last but not least, in my lab in West Lafayette, Indiana, to my students and staff that helped me carry this research. And with that, I open the forum for questions. Thank you.
Thank you very much, Javier. Always nice to learn about the feedstock sources I haven't heard of before. So incredible what masses you're talking about. I had one quick question. So how heavy is a railroad tie?
About, once they are used, about 86 kilograms.
86 kilograms. And also you got a question about how does creosote looks like? Is it a tar or what's the application? How do you apply it to the railroad tie in the first place? So
there's under pressure. The ties are under pressure in tanks, and that's something I'm not very familiar or not my area of expertise, but they seem like they impregnate these ties under pressure. So they, at the end of the day, once they do this treatment, the railroad tie has about 9 kilograms of this creosote. So it's a large operation when they do that. But again, I'm not very familiar, and that's not my expertise.
Yeah, because I just, you got one follow-up question on that, and also for myself. Did you check if the creosote is concentrated on the outside of the railroad tie, or is it homogeneously distributed?
The way I understand is that it's distributed to the whole tie.
Oh, okay.
Because it's under pressure.
Okay.
When they add the creosote mixture.
And the follow-up question from the audience was, did you also look at pyrolysis of smaller chips instead of the relatively large chunks that you used?
No, we have not. I guess that's something that we can look at further.
Yeah, because so the mentioning was because it could potentially improve the thermokinetics and drive more of the pHs out.
Yeah, so for our type of work that we did at 700 degrees, it was impressive how much is left in the biochar. It's pretty much is non-existent. It's only 20 milligrams per kilogram of biochar. So it's not much. And when we did the leachability test and toxicity test, we couldn't see much at all on the biochar. So I think just from that point of view, I believe we pretty much remove almost everything. If probably a lot of those 20 milligrams of semi-volatiles may be embedded so inside the biochar. But again, that's something further studies need to be done on that.
Okay, and then so the other questions were related to the extraction or to the two phases that you have in the condensate.
Yeah.
So John was asking, was either of the two phases of the volatiles water soluble?
I'm not sure. That probably something I may ask Vera, our next presenter, but that's something we didn't do.
Yeah, because the next question was if the moisture content of the upper phase, what was the moisture content? Because typically you have a aqueous phase on top. So that would be a follow-up question. And also what if the tar phase was water insoluble, if you know that?
I doubt it will be water because it's heavier. I don't have the density right now with me, but it's about 1.01 or 1.05 or something like that.
Yeah.
But perhaps there's some water in there.
Okay. Then Stenning Larsen was asking, did you do any analysis of the non-condensable gases products during pyrolysis, and especially if you found dioxin in there?
I'm sorry, can you repeat the question?
For the non-condensable gas fraction, that did you do any analysis on that one?
No, we didn't do that.
And Michael was asking, have you compared the remaining pollutants in the biochar to any states limits for land application?
Yes and no. So we in the United States, as last time I checked, we don't have much of the updated concentrations for what's the limit. So when we wrote the paper on this at 700 degrees Celsius, I based everything based on the European limits. So at least from the European limits, biochar is good to apply, at least in the European limits. But here in the States, as far as I know, we don't have that. We have one guidelines from the 70s or something like that from the US EPA, but again, it's from the 70s. So probably it's obsolete already.
Okay, I don't know who is sharing his or her screen. So the last question was a bit unrelated to your presentation, but you might still be able to answer it. Which was, do you know of any labs that do characterization of biochar in Mexico?
No, I'm not familiar. Sure, I'm from Mexico, but honestly, I don't know, and I wish I knew. But they can contact me. We can see what we can do.
Okay, great.
And I guess at the end of my presentation, I have this QR code, so that has my information in there.
Okay, perfect.